This is a study of titrating acids with bases, and we want to see how is it that the pH titration curve gets the characteristic S shape. We start off with a definition of normality. The normality of a solution is the molarity multiplied by the number of protons that the acid is giving off, or by the number of protons the base takes in. For example, hydrochloric acid is monoprotic, HCl. 1 molar hydrochloric is also 1 normal hydrochloric because each mole of HCl gives off 1 mole of hydrogen ions. But 1 molar H2SO4 is 2 normal because sulfuric acid is diprotic, H2SO4. As it's titrated, it can give off 2 moles of protons for every mole of H2SO4. This is the apparatus that we usually see in a titration. We put a solution of known normality in the burette, and at the end point of the reaction, we record the volume of the solution that we have used. A solution of known volume but unknown normality is in the Erlenmeyer flask below, and the stopcock controls the entry of whatever is in the burette to the Erlenmeyer flask. We're going to assume that a strong or weak acid is in the flask and that we want to find its concentration. So we would titrate with a strong base, typically sodium hydroxide since it's not expensive. And we would have already figured its normality. Generally speaking, we standardize that with potassium acid phthalate, a dry, weak acid. Let's talk about what happens at what I call stage 0. We're going to work with a volume of 0.010 molar NaOH. We start off, 0.010 molar hydrochloric acid is the only thing in the flask here. And we'll start off with 25 milliliters. I think it's obvious that the pH, the negative log of this, is 2. There are 0.25 millimoles, 0.01 times 25, of hydrochloric acid in the flask. At stage 1, we're going to add 10 milliliters of 0.01 molar sodium hydroxide. That's 0.10 millimoles of sodium hydroxide, 10 times 0.01. This is going to neutralize 0.1 millimoles of the hydrochloric acid. So we subtract that from the original 0.25 millimoles, and that gives us 0.15 millimoles of hydrochloric acid in the flask in a volume of 35 ml. We find the concentration by dividing the 0.15 millimoles by 35 milliliters, and we get 0.0043 molar HCl. We plug that into our calculator to take the negative log of that number, and we get 2.37. So the pH hasn't gone up very much, even though we've added 10 milliliters of the base. At stage 2, we add 10 milliliters more of the base, neutralizing another 0.1 millimoles of the acid, leaving now 0.05 millimoles of HCl in the flask, in a volume of 45 milliliters total. The concentration is the 0.05 that's left divided by 45, or 0.0011 molar. Take the negative log of that, we get a pH of 2.95. We have still not changed it very much from the original 2. I call this stage 2.9. We're going to add 4 milliliters of the base. That's 0.04 millimoles. That'll neutralize an equal number of millimoles of the acid, leaving only 0.01 millimoles of HCl in the flask and 49 milliliters. We keep adding water as we add the base. Concentration now is 0.01 divided by 49, or 0.0002 molar. Now we do the pH, negative log, and we find it's 3.69. It has risen appreciably. At stage 3, we call that the end point. We add another milliliter of the base that neutralizes the last millimole of the acid, leaving 0 excess millimoles of HCl in the flask. There is now 50 milliliters of total solution in the flask. There's no excess acid or base. It's just sodium chloride, a neutral salt that does not hydrolyze. So the pH is the pH of salt water, 7, a neutral pH. And as you can see, the pH is shot up from roughly 3 to 7 with 1 milliliter additional NaOH. At stage 3.1, we're going to add another milliliter of the sodium hydroxide, 0.01 millimoles. The acid's gone, so that leaves the base undisturbed in 51 milliliters. We divide that 0.01 millimoles by 51 milliliters, and we now have 0.00020 molar hydroxide ion. We now have to calculate the pOH by finding the negative log of this number. It's 3.71. We subtract it from 14 and get a pH of 10.29. So that next milliliter of base added has driven the pH up another 3.3 units. Stage 4, I call this excess base. We add now 4 milliliters of the 0.01 molar NaOH. There's no more acid, so we now have 0.05 millimoles of sodium hydroxide undisturbed in the flask in 55 milliliters. We divide the millimoles by the volume. We get a pOH of 3.04 and a pH of 10.96, a small increase. At stage 5, we have more excess base, 10 milliliters more of the sodium hydroxide, leaves us 0.15 millimoles of sodium hydroxide when we add what we already had in it. The volume is 65 ml, so we calculate the hydroxide concentration and the pOH. The pH is 11.36. We can see now that we have the classic S-curve forming up. Finally, we're going to add the last 10 milliliters of base to finish up the titration, having added 50 milliliters. And we now have a volume of 75 ml, hydroxide concentration. All the base is still there, and we find a pOH of 2.48 and a pH of 11.52. The S-curve is complete. This is a graph of what we just saw, connecting the dots, of course. This function is irregular, so that's how we did this. There is a rapid change in pH before and after the end point, as you can see here, going from 3.15 to 3.87 to 7 to 10.12. This explains how the pH can make such a huge increase in the vicinity of the end point, going from about a 3 to a 10 in just 2 milliliters. Now the indicator that you choose should change colors about the pKa of the salt that's formed. Here we're forming sodium chloride, which has a pH of 7. But if we had an acidic salt being formed, we'd want something that would change the color somewhere down here in the acid range. If we had a basic salt like sodium acetate, we'd want something that changes colors maybe around a pH of 8. So your titration of HCl with sodium hydroxide, if you chose phenolphthalein, that's a good choice. It changes around 10, and with that last drop of added base, it'll shoot past 10 as it makes this huge increase here. Here's a nice table of indicators and the pH that they change at. That's published on the internet. by the chemics people. If you're titrating a strong acid into a weak base, what indicator would you choose? Remember, the tug of war is going to favor the acid. My choice would be methyl orange.